Hello everyone, my name is Glenn Evenbley. I'm a professor of physics at Georgia Tech. I'm here today to demonstrate the TensorTrace app, which I've designed to facilitate the implementation of tensor network methods. So my goal here today is not to explain the theory behind what tensor networks are and how they are used. Please see the links in the video if you'd like to learn more about these aspects of tensor networks. The purpose of TensorTrace is to automate the contraction of tensor networks as much as possible. Okay, it allows you to draw tensor networks using a drag and drop functionality, but then the software will do all of the hard work of solving for the optimal contraction order, figuring out the cost associated with the contraction, and even generating the code in MATLAB, Python, or Julia, which will allow the contraction of the tensor network. Okay, so let us begin. The first example I'm going to do is for the contraction of a matrix product state with a two-site unit cell. Okay, so I'm drawing a tensor. So here, each of the numbered plaquettes, which I call anchors, represent an index of the tensor. So these can be moved around within the tensor itself. So here we have a 3-index tensor. Going to give this a name. I'm going to call this A. And you see we have a bunch of options. We can change how this tensor appears. So this is the first tensor of my matrix product state. So I'm just going to duplicate this by right-clicking and dragging. I'm going to rename this second tensor as B, and I'm going to give it a different color. Okay, so these are going to be the two tensors of my matrix product state. I'm going to select them, going to duplicate them again, and now I'm going to flip them and we're going to conjugate them. Okay, so this is the bra and the ket of my tensor network. So these are the tensors involved in the contraction. I'm now going to duplicate this network because I want one representing a contraction from the left and one representing a contraction from the right. So this one is from the left. I'm going to call this tensor row L. I'm going to reduce the number of anchors to 2, and it's going to have 1 and 2 and a different color. And then we're going to have one on the other side, which represents the contraction of the MPS coming from the right hand side. So we are now ready to join these tensors with indices in order to form networks. So let's go over to the indices tab over here. We see we have 4 different indices available to us. So these represent different dimensional indices within the network. Okay, so for each index we can give it a name. We're going to call this one chi, representing the virtual dimension of the MPS. We're going to call this one D, representing the physical dimension. Okay, so we can also associate a default dimension with these indices, which the program will use when it determines what the optimal contraction order is. Okay, so D is usually small, we'll keep that at 2. Chi is usually the larger index, we'll set that at a default dimension of 20. Okay, so in order to join tensors with indices, we just click on an anchor, then click on another anchor to complete the index. So we'll start off by making all our chi dimensional indices. There we go. So these are the internal indices. If we want an open index, then we just click on an open space. Okay, so now we have different open plaquettes. These represent the open indices of our tensor network. Okay, so this is the first open index and the second open index. And we can change this ordering. If I hover over a plaquette, I can just press any of the numbered keys on the keyboard to change the open index number if I so choose to. Okay, so let's create the d-dimensional indices for each of our networks and the chi-dimensional indices for the second one. Whoops, there we go. Yeah, there. Okay, and I need to change the index orders of the second one. Okay, so we have 2 different tensor networks. We're now ready to export these to code and to figure out the contraction orders, etc. Before we do this, we have to tell the program that we're dealing with 2 distinct tensor networks. I'm going to select everything from the first network. I'm going to say this is tensor network 1, and now it's denoted that this is tensor 1.1. Similarly, I'm going to select the other network and assign this to network 2. Okay, so now we're ready to export these to code. We click export to code. What the software has done is automatically looked at each of the networks, checked that they're a valid network, it's determined the optimal contraction order of the networks. So now we see the cost in terms of scalar multiplications required to evaluate each network. We see the optimal contraction order is given to us, and we see the leading order contraction costs as a function of the indices we have. So this one is chi to the power of 3 times local dimension d. Okay, and we can now, so we have seen that we have two networks. It's found the costs of both of them. We can now generate code in one of our preferred languages, which will automatically contract these networks. Okay, so that completes the first example. As a second example, what we're now going to do is build all of the networks necessary to contract a binary MERA in one dimension. Okay, so I'm going to start by making my disentanglers. So these are 4-index tensors with the following index orders, and I'm going to call these U. Okay, so we have two of them side by side. We now have our isometries, which are 3-index tensors. I'm going to call W. So 1, 2, and 3. And we have 3 of these appear in the networks we need to contract. Okay, so we have a Hamiltonian term, which lives here, which has 6 indices. I'm going to call little h. And the indices 1, 2, 3, 4, 5, 6. Red. Okay, so those are the tensors from the kit. We need ones from the bra as well, which are again flipped and conjugated. They line up here. We now need one final tensor for the density matrix. This lives on top. This has 6 indices. Okay, and they go 1, 2, 3, 4, 5, and 6. Okay, and this one we're just going to call R, or row. Okay, so now we're ready to join this network with indices. Here we're going to have an index of chi, and an index we're going to call chi p, for chi prime. Okay, so chi we're going to give a default dimension of 8. Chi prime is a default dimension of 6. This is usually the smaller one. Okay, so let's make our chi dimensional indices. Usual. And we just had an autosave come up there. We're doing our chi prime dimensional indices are the ones in between the disentanglers and the isometries. Like that. And we have some final chi dimensional indices. Okay, and I have ones which connect the top and the bottom of my network. So I could just leave it like that, but that looks kind of ugly with overlapping indices. Fortunately, I can drag the control points of an index to make a curved index, so I can avoid overlapping lines, at least in one-dimensional diagrams. Oops. Didn't want to do that. So this index I wanted to move out a little bit. There we go. And we'll create the final curved index, which goes all the way over here, like that. And that is good. Okay, so this is one of the diagrams we need to contract a binary MERA. What we're actually going to do is take the whole thing and duplicate it, so the second one looks the same as the first one, except the Hamiltonian term is shifted over to the other side. So I'll just reconnect the final indices, 1, 2, and 3, and connect this one to here. Okay, and here we have completed all of the diagrams necessary in order to contract a binary mirror. So I'm going to call this network 1 and this network 2. Okay, so in this case, these are both closed tensor networks. There are no open indices. But when we actually export the code and it searches and it finds the optimal order, the code it will generate will not only contract these closed tensor networks to a scalar, but will generate all of these single tensor environments from these networks. Okay, so the code we could export right now would be the complete set of diagrams necessary to contract a binary mirror, to optimize a binary mirror for the ground state of some system. So hopefully this example has convinced you of why this TensorTrace app could be very useful to you. So making networks such as these the old way, doing everything manually, figuring out contraction orders manually, programming each one manually, this could take several hours or several days of work, even if you're very experienced making these tensor network codes. Okay, so here it only took a few minutes and we're done with this relatively complicated tensor network algorithm. So more information about how to use the software and the software itself is found at tensortrace.com. This is still something in development, so please send me any feedback or suggestions. Would be appreciated. Thanks a lot.